So just for the pre-labs for our upcoming lab, do we just have to pretty much answer the pre-lab questions and don't really need context or anything?
Yeah, it's not meant to be something that takes a ton of time. Yeah. But I mean, you should write an understandable solution.
Oh, yeah.
Yeah. Oh, here we go. It's so yeah, just while we're waiting a few seconds, my plan is for, some of you did the first day of experiment 1 yesterday, some of you will do it today. Then we'll do experiment 1 day 2 next week. And what I'm going to do is that the sign up sheet for the experiments, I'm going to add new tabs. And so there'll be 2 new tabs for experiment 2 sign up. There'll be a tab for the LO1 lab section and one for the LO2 lab section. And so I'll just get you to sign up for experiment 2 using those new tabs. And what we'll try to do is we'll try to make sure that everyone signs up for experiment 2 before they leave the lab on day 2 of experiment 1. Okay, so that's the plan. All right, so let's get started. What we were talking about was Fourier series. A lot of the discussion to this point has been a little abstract. And so today we're going to do an actual example. And so let's see how that's going to work. So we were going to imagine any periodic function. And the claim is that we could express it as some constant plus a sum of cosines and sines where the terms keep getting higher and higher in frequency. So we'd have like 1x, a 2x, a 3x, a 4x terms for both the cosine and the sine series. And we needed a prescription for finding the values of the constant and the 2 coefficients, an and bn. And so we developed that. So a0 was found by evaluating the integral of f of x dx with a 1 over pi out front. An was found by a similar integral, but we multiply the f of x by cos nx, sorry, and then bn is we multiply by the sine nx. Okay, and we haven't done any examples so far, and what we're going to do today is our first example. And the example we're going to do is a square wave. And so let's see if I can find my notes. Here we go. Okay, so the example that we're going to do is we're going to try to write down the Fourier series for the following square wave. Our square wave is going to oscillate between 0 and 1, and it will have a period of 2 pi. From minus pi to 0, it will be 0, and then from 0 to plus pi, it will be 1. And then that is just going to repeat over and over again. So this is one way, another way of defining the function instead of drawing the picture. We'll say on the interval from minus pi to 0, the function is 0, and from 0 to plus pi, it's 1, and then you just have to repeat that over and over and over again. Okay, So let's start by finding a0 is this integral of f of x between minus pi and plus pi, and then there was a coefficient of 1 over pi out front. All right, so for this f of x, we're just going to use this definition of this function, and so we say, well, it's a piecewise continuous function, so let's separate the integral into two parts. So a0 is going to be 1 over pi times, let's see, it's going to be the integral from minus pi to 0 of f of x, but on this interval, f of x is just equal to 0, so it's just 0 times dx plus the integral from 0 to plus pi of f of x, but on this part of the interval, f of x is just equal to 1, so this is 1 times dx. Okay. The integral of 0 is 0. This integral would evaluate to pi, because when we integrate the dx, we'll just get an x evaluated between 0 and pi, so that's just pi minus 0 is pi. And so then overall, we get 1 over pi times pi. And so therefore, this a0 is equal to 1. And so that's one of our coefficients. And now what we have to do is we have to try to find the an coefficients, which is a similar integral, except for we multiply by the cos nx. Again, we're going to do the piecewise continuous integral, so we'll break it up into two parts, minus pi to 0, and then f of x is equal to 0 times cos nx dx plus 0 to plus pi. On this part of the interval, the function's equal to 1, and then we have cos nx, and then we integrate. Okay, this part's still 0. It doesn't matter that we're multiplying by cos nx, it still has a 0 out front. Let's see if we can do this. Well, this is going to be the cosine will integrate to the sine. And so we'll pick up a 1 over n from the integral. So this would be 1 over pi times n sine nx from 0 to pi. And so let's just be, for this first example, let's just be detailed. Okay, so sine nx, oh, let's see if I can close this. Yeah, there we go. All right. So sine nx evaluated between 0 and pi. So it's going to be sine of n pi minus the sine of 0. What's the sine of 0?
0.
Yep. And what's the sine of n pi, where n is an integer, like sine of pi, sine of 2 pi, 3 pi, so on, 0. And so we end up with, therefore, an is equal to 0 for all n is 1, 2, 3, and so on. Okay, so what we've figured out so far is that a0 is 1, the constant that's out front. All of the ans are 0, so these are the coefficients of the cos nx part of our Fourier series, and so they all completely vanish. We know that the square wave is not a constant, so we better hope that when we do the bn coefficients, we get some non-zero results. Okay, so bn, I guess we could highlight this as one of our results. So bn, whoop, is going to be 1 over pi, the integral from minus pi to pi of f of x sine nx dx. So we do everything that we've been doing before. we separate our integral into the two pieces. Here's the second part where the function is equal to 1. Okay, this one's going to be 0. And so Bn is going to be equal to 1 over pi times n. So the sign is going to integrate to cos, and I guess it's going to pick up a minus sign, isn't it? So this would be minus cos nx, and then we have to evaluate between 0 and pi. Okay. So this is minus 1 over n times pi, and then it's cos of n pi minus cos of 0. Okay, cos of 0 is 1, so this is going to be a 1. And let's see, cos of n pi, let's just make a little table. So if n equals 1, we get cos of pi, which is minus 1. If n equals 2, we get cos of 2 pi, which is plus 1. And then we're just going to get this alternating plus minus 1. And so let's think about, let's see, minus 1 to the power n, where if n is 1, we'll get minus 1. And then if n is 2, we'll get plus 1, minus 1, plus 1, and so on. And so what we could do is we could re-express this cos n pi as minus 1 to the power n. All right. And so let's see how these coefficients work. So what does Bn look like? So we have a minus here, and then we have a minus 1. So if we bring the minus sign inside, we'll get a 1 over pi times n. And then let's see, we get 1 minus 1 to the power n. So those are our Bn coefficients. And let's see what they end up looking like. So this is n and Bn. So we'll make that a bit smaller. So we'll do a few of them. Okay, let's try n equals 1. So we'd have 1 minus, then n equals 1. So we're going to have a minus 1 to the power 1 is minus 1, but we have the minus 1 outside. So I think we get 1 plus 1 in this case. And so then we have 2 divided by pi times n, but n equals 1. So I think this is 2 over pi. Okay, and then we do n equals 2. Minus 1 to the power 2 is plus 1. So then we have 1 minus plus 1. So we're going to get a 0. And in fact, anytime n is even, we'll get a 0. All right, so let's try n equals 3. Minus 1 to the power 3 is minus 1. So we get 1 minus minus 1. So that's all is a 2. So we get 2 divided by pi divided by n equals 3. So this would be 2 over 3 pi. This one would be 2 over 5 pi, and so on. So for n even, Bn is equal to 0. For n odd, Bn is equal to what? It's 2 over n times pi. Okay, so, and we also know, okay, so that's our third result. So now we have all of our results. We have a0 is equal to 1. All other an are 0. All Bn with n even are 0. And for the odd ones, we end up getting this. So the Fourier series for our square wave is, okay, let's see. Let's just write down the generic Fourier series. It was A0 over 2 plus the sum from n equals 1 to infinity of an cos nx plus bn sine nx. And let's just write out some of those terms. So for our square wave, A0 was 1. So we get 1 divided by 2. So we get 1/2. We don't have to write out any cosine terms because they all vanish. So we only have to write out the odd Bn terms. And all of the odd Bn terms are going to have 2 over pi. So I'll put my 2 over pi here. And then we'll write out the odd terms of sine nx. And we just have to remember that we have to divide by n. So for n equals 1, we're going to get just sine x. And then for n equals 3, we'll get 3x divided by 3. And then we'll get 5x divided by 5, plus and so on. And so we'd have to keep writing out more and more and more of those terms. And so that's the claim, is that this is a representation of a square wave. And it's not at all obvious just looking at this that this does produce a square wave, but we can test it because it's easy to plot these terms. And so let's just make that plot. And in fact, I have it made here. And so let's see. Okay. Let's do it this way. Let's see if I can pull it up here. Here we go. No, sorry, that's not what I wanted. This one, I think. All right. So 232. All right. Constructing a square wave. All right. So I posted some of these notes on the course website. And so this is just a Jupyter notebook. And so all I'm going to do is I'm going to use it to try to plot this result for our square wave. This is exactly what we just wrote down. 1/2 plus 2 over pi sine x, 1/3 sine 3x, 1/5 sine 5x, and so on. Okay. And so what we're going to do is we're just going to keep adding more and more terms. So the first thing I'll plot is just 1/2 plus 2 over pi times sine x. And that's obviously not going to look like a square wave. But let's just plot it and we'll just see how this plot evolves as we include more and more terms in our Fourier series. Okay, and so here it is, 1/2 plus 2 over pi times sine x, and it's just a sine wave, that's all it is. Okay, then we're going to do a second plot. The second plot has the sine x term, but it also has the 1/3 sine 3x term. Okay, and when we plot that, it's still not a square wave, but these are a little more steep and these are a little more flat. Okay, and so here this plot just shows the two of them together. All right, and then we make a third plot where we're going to have sine x, 1/3 sine 3x, and 1/5 sine 5x. Okay, and that's the green one. And again, these vertical parts are getting steeper, and these parts here at 0 and +1 are getting a little flatter. Okay, and so there they are, everything together, and you can see the green one is the most square-like. How long do I keep doing this? Okay, so I'm going to add the 7th, 1/7 of sine 7x. Okay, so there's the plot and there's everything together, and the yellow one's looking a little more square. But of course, it still doesn't look like a perfect square wave. So what we're going to do is I'm going to write a little loop that's gonna include terms up to n equals 30. So the Bn has only the odd terms, and so there is no n equals 30. So this includes up to n equals 29. So this would go to 1 over 29 times sine of 29x. Okay, and there's this cyan one. And so now this is really vertical, almost a slope of infinity. And then this gets quite flat. There's still some oscillations in there, but compared to all of these other approximations, this one's getting quite close. Okay, last thing we're gonna do is we're gonna use the same for loop to add up a bunch of terms, but we're gonna go up to 10,000. Okay, and for something like Python, like, you know, if I was to plot that by hand, I would die before I finished, but Python does it in an instant. Okay, and so that's the result when you add up all of these sine waves, keeping terms up to 9,999 for Bn. So this is 1/2 plus all the odd parts of sine x, sine 3x, 5x, up to sine 9999x. And so there's your perfect square wave. All right, and you could do this for any type of periodic function, and you have an assignment, as a matter of fact, where you are going to do that. So just so you know, assignment 1 is on the course website. It showed up there, you know, maybe on Sunday or something on the weekend. Let me just open it up. So you've got 3 problems, I think, that are going to be graded. In our notes, we said one of the things you were going to do was to confirm this integral cos mx, cos nx for all the cases m and n are both 0, m and n are equal to each other but not 0, and m and n are not equal to each other and not equal to 0. Okay, and then the second question is to confirm that the coefficients of Bn are in fact given by this expression. For that, you could follow exactly what we did in our notes for the An calculation. And then you have question 3, where you're given some periodic function and you have to find the Fourier series like we just did for the square wave. Just so you know, there are extra problems. They won't be graded, but they're extra practice if you want to try them out. Okay, good. And then the due date is Wednesday, January 24th at the start of this class. So it's next week on Wednesday. All right. Good. Any questions about any of that stuff? Yeah, that's right. So just write out your solutions and then staple them and hand them in at the start of class. Yeah.
Is there a way we can get them online?
No, I need to get them graded. So I need to get them to the TA to get them graded. And so I need paper copies. Yeah. All right, good. So let's see, we're supposed to go to 11:50. All right, so we have about half an hour left. So what we're gonna do is the reason we did this Fourier series stuff is because it's relevant to the, in particular to the thermal waves experiment, but it's also relevant to experimental physics. Like often you measure things as a function of time, where you kind of acquire a signal on an oscilloscope or something like that. But there are other instruments that are called spectrum analyzers that will measure quantities as a function of frequency. So we were talking about musical instruments last time, and if we measure at what frequencies does this instrument oscillate and what are the relative amplitudes, that's like the spectrum of the instrument's output, and you have instruments that can make those measurements as a function of frequency. They're called spectrum analyzers. If you go on and take the 3rd and 4th year labs, there are some experiments that actually use these spectrum analyzers. But what we're going to do for the rest of the term is we're going to talk about methods for treating and understanding uncertainties in measurements. And so that's what we're going to do starting from right now. So in any measurement of a quantity X, we must determine from the experimental conditions an estimate of our confidence in the value, in the, let's say in the measured value. And so our confidence or our uncertainty estimate might be delta X, uncertainty in the measured result. And so it's pretty important actually for the development and advancement of science in that, you know, in particular in physics, really, if you develop some theory, it really only has a lot of value if you can go out and make measurements that either confirm or reject the assertions of this theory. So usually someone will develop a theory and then they'll say, okay, we know some previous results and my theory matches those results, and it gives a pretty good picture of what people have measured in the past. But my theory also makes predictions for what should happen if we were to, I don't know, measure this as we cool it down to some low temperature. And so if someone goes and does that experiment and the theory will either be confirmed or rejected, if it's rejected, then the theory is either thrown out or modified in some way. But if you're going to make those decisions, you have to know the experimenter measured a value of 6.8 and my theory predicted 7.5. So if 6.8, how do I compare 6.8 to 7.5 unless I have some estimate of the uncertainty in the measured value? If it's 6.8 plus or minus 1, then it's going to be consistent with 7.5. But if it's 6.8 plus or minus 0.1, then it's not consistent with 7.5. And so really to make these kind of judgments, these uncertainty estimates are important. They're also, they can be tedious, the calculations can be long, but it's really necessary. All right, so what we're going to talk about is the different kinds of uncertainties we might encounter. So two terms that I want to define to start are accuracy and precision. So accuracy. Accuracy tells us how close a measurement is to the true value. And then we have precision, which is going to tell us how much fluctuation is there in repeated measurements. So if I do an experiment and I measure some quantity X, and then I do that same experiment over again, I'm going to get a different value of X. And every time I do it, I'll get a new result for X, and they're never going to be exactly the same. So how widely those results are distributed tells us about the precision of our experiment. So we could make some plots here. Let's suppose that I was going to make a measurement of Y versus X. So Y is whatever the conductivity of a metal and X is the metal's temperature. So as I cool down the metal, I keep measuring these conductivity values and I make some plots of that. And so maybe my data looks something like this. Well, actually, let's just draw them as little points here. And so maybe there's some scatter in the data, but they follow this kind of linear trend. And then we compare that to some like true value, might look something like this, true value. So what we would say about this kind of data is that the precision is quite good because there's not a lot of scatter about a straight line that we could draw through these data, right? If I draw a straight line through the data, I would say there's not a ton of scatter about that line. And so that means there's not many fluctuations. And so we have high precision here. But if I compare my measurements to the true value, I would say that they're inaccurate because there's a constant or a consistent offset. So we would say that this is a precise but inaccurate measurement. So a precise but inaccurate measurement. Now, it's often the case that it would be hard to judge whether a measurement is accurate or not, because if I already knew the true value ahead of time, what's the point in doing the measurement? Why would I spend time measuring something when I know exactly what I'm supposed to get? There are some cases where you might do that, like you might be designing an experiment, and what you first do is make a measurement of something you know to test the quality of your apparatus. And then once you're sure that you have that you have that confidence in it, then you go make some new measurements with the same apparatus. You trust it now, but now you're measuring some new material or some new phenomenon where you don't know what the true value would be. Okay, and then we could have a different kind of measurement where we measure y as a function of x, and this time when we make our measurements, they're kind of scattered all over the place, but they're scattered kind of symmetrically about some true value. And so here we would say we have large fluctuations. So it's an imprecise measurement, but it's accurate because it's scattered symmetrically about the true value. So this is an imprecise measurement. Well, let's say imprecise but accurate. Okay, so what we can say is that the accuracy of an experiment is largely determined by systematic errors. Okay, so systematic errors are errors that are reproducible. So for example, you might have like a pair of digital calipers, and then you're going to measure the length of a block over and over again. And you do a set of measurements, and then at the end, what you do is you've done all your measurements, you take your calipers, and then you close the jaws of the calipers, and you look at this digital display, and it says 0.006, and you're like, well, hold on. This is closed, I should be measuring 0. Why are you showing me 0.006? And then you would realize that, well, I haven't properly zeroed my calipers. All of the previous measurements I just did have a 0 of 0.006. And so they're going to be overestimating the true width. My measurements overestimate the true size of this block. And so I have to subtract that offset off. So that's an example, like a simple example of a systematic error. So these are errors that make a result reproducibly different or offset from different than the true value. Okay, so another example besides just calipers that haven't been zeroed properly is, you know, maybe you're measuring the time it takes a ball to fall a certain distance, and so I guess what could happen is you go 3, 2, 1, and then on 0, the person starts a stopwatch, and then you hear the ball hit the ground, and then you start the stopwatch. And so maybe your time reaction for the sound of the ball hitting the ground is very good. But maybe 3, 2, 1, and then release. Maybe your friend is releasing the ball, and then you're starting this, and there is some bias where 3, 2, 1, go, and then like maybe the person with the stopwatch is always a little slow to start the stopwatch, and so they measure a fall time that's too short consistently. That's another type of systematic error that if you knew that it existed, you would correct it. So examples of this are faulty equipment, like our calipers that haven't been calibrated. So uncalibrated calipers. Or it could be something like bias. And so your bias might be like, I'm start my stopwatch too slow all the time compared to when my friend releases the ball or something, like a slow reaction time that's reproducible. That kind of thing. Or, you know, a worse kind of systematic error is if someone's looking at data and they're kind of making decisions about how to analyze it to try to get it to agree with some predetermined, I don't know, theory that they're trying to confirm or something like that. So that's a more dangerous kind of example. Okay, so if you are aware of a systematic error, you would correct for it. So for the calipers, when you find out that it's not zeroed properly, you don't have to redo all your measurements. You just say, okay, I have to subtract off the 0.006 from all of my other measurements. Or once you realize that your reaction time is not synchronized with when your friend is releasing the ball, then once you realize that, maybe you study it and you figure out, okay, by how much is the time of flight too short, and can I correct all my previous measurements for that? So once the systematic error is identified, then you work hard to try to solve that error and either repeat your measurements or correct the measurements that have already been done. So this is not the kind of thing that we're going to be talking about in this class, because this really has to do with experimental design. And so you want to design and test your experiment so that you eliminate as many of these effects as possible. Once you've done that, you're left with the random fluctuations, which determine the precision of your experiment. And that's the kind of thing that we're going to talk about. Okay, so we had systematic errors, and now we have random errors. Okay, so these determine the precision of an experiment. So Example, let's go back to calipers. We measure the length of a block of wood with calipers. Even if we've eliminated all the systematic errors, right? We've zeroed the calipers properly. There's no like dents or dings on our calipers. Every time we make that measurement, we're still going to get a slightly different result, right? You kind of close the jaws, check the zero, you make your measurement, then you write down the results, you close the jaws, measure again, write down the result, and you do this over and over and over again. And every time you get a slightly different number. Okay, we won't get the same reading each time. We instead get a distribution of values. And we can plot that distribution of values as a histogram. And if you take a very large number of measurements, that histogram will look like a normal distribution or a bell curve. And so it would look something like this, where you'll get a large amount of measurements near the center of this distribution. So maybe this is the average value of the length, sits near the center. But sometimes, for whatever reason, for random fluctuations, you get some that are well below that average or well above the average. But those events aren't so frequent. And so they're in the distribution, you get small out in these tails, and you have a big peak near the average value. And so maybe this is measured with our calipers. All right. So the only way that you can improve the precision of your measurements is by coming up with a better experimental setup. So you could buy better equipment, or you could be clever in how you design your experiment. And so let's imagine we take this block, and now what we're going to do is, instead of using calipers, what we're going to do is we're going to measure, we're going to reflect the laser off of it, and we're going to measure the time for the laser to travel from the source to the block and then back to a detector. All right, and so let's see what would happen. So reducing random errors is achieved through better experimental design, or improved equipment. So let's do an example. We use a laser and a photodetector to measure the length of our block. Okay, so what we could do is we first take our laser and we shine it at a wall, and we let the laser reflect off the wall, and then it hits a detector. So this is maybe our detector. And so let's imagine that this length is something like length L. Okay, and so we measure the time from when we turn the laser on till it hits the detector, and that time is given by the speed of light, or I guess it's twice the length divided by the speed of light. So then if we know the speed of light and we measure the time, then we could get this length. And then we say, okay, now what we're going to do is we're going to have the same setup, but I'll put my block over here now. And we'll say this is still the length L. And I'm going to take my laser over here. I'm going to shine it off of this block, and then it goes to my detector. Whoops. Detector, laser. And maybe this length is X. And so now I measure the time of flight. This time, the time of flight will be 2 times L minus X, or I guess, yeah, this would be L minus X, and this would be L minus X. So it's L minus X all times 2, divided by the speed of light would tell us the time. And so from the difference in these 2 times, I could deduce what the value of X is. And if I have very precise, very fast electronics, then I could do that measurement very accurately. And if I made a distribution of those kinds of measurements, then maybe it would look something like this instead. So it would be still a distribution, like every time we do a trial, we're going to get a different value of X, but maybe those values are really concentrated very closely to the mean compared to what we had for the calipers. And so what might happen is as we make our experiment more and more and more precise, then there's other effects that we have to start to think about. So for example, just a sec, if the temperature of the room is changing in the laser experiment, you know, if the room gets hotter, the block will expand thermally, and that will make X a little bit bigger. And if our experiment's sensitive enough, we'll be able to detect that stuff. So then we have to say, okay, now what I have to do is I have to control the temperature of my block so that it's always 25 degrees Celsius. And when I report my result, I'm going to have to give the length at exactly 25 degrees Celsius. And so all these other effects start to become important. Yes, did you have a question?
Is it always the case that when you reduce the random errors that it centers more around the average?
If the errors are really random, so what random means is that it's just as likely that you'll measure something below the mean and then above the mean. So if you plot a distribution and your uncertainties or your errors are really random fluctuations, then you will get a symmetric distribution. And so yeah, it will be symmetric about the mean. Yeah. Yeah. Anything else? No. Okay, good. So we have a few minutes left. I guess what we'll do is we'll begin to talk about distributions of measurements. So we talked about repeating these experiments over and over and over again. Let's begin to talk about distributions. And we'll do this through an example. So you have a radioactive sample. So this is just some material that maybe emits electrons, maybe it's doing beta decay or something like that. So that emits electrons. So beta decay. Okay, so in this radioactive element, maybe this is element N. And so A is the number of protons and neutrons. It's the number of nucleons. And Z is the number of protons. And what this element does is it becomes some new element, N prime. And the way that it does it is it converts a neutron into a proton. So to make a neutron become a proton and still conserve charge, it must emit an electron. So we have the same number of nucleons, the number of protons and neutrons is the same. We're just going to take one of the neutrons and increase it to make it a proton. So Z increases by 1. And then we get an electron emitted. And in fact, there would be also a neutrino. Okay, so what's happened really is a neutron has decayed into a proton plus an electron, and a neutrino was emitted in process, or an antineutrino in this case. So what we're going to do is we're going to sit there beside our radioactive sample, and we're just going to count the number of electrons that are emitted during some fixed time interval. So maybe we sit there and every 10 seconds, we count the number of electrons that are emitted. So you measure the number of electrons in a fixed time interval to determine the beta decay rate. Right, and so we sit there for 10 seconds with our instrument and we say, okay, we do trial 1, 2, 3, 4, 5, and so on. And it keeps going to like up to trial N. Okay, and so we get 12 measurements, then 18, then 13, and then 17, and then I don't know, 22, and then here we get 8 or something like that. All right, and so what we could do with this data is we can plot a distribution. And so we make our distribution through a histogram. And so we say, all right, I'm going to bin my data. So every time I got 12 or 13 counts, that's going to be in one bin, and I'll count how many times I got a 12 or a 13. In the next bin, I'll count how many times I got a 14 or a 15. And then I count how many times I got a 15 or a 16. So we construct a histogram by binning the data and counting the number of trials that fall within each bin. So for example, bins could be like 12 and 13, and there could be a bin that's 14 and 15, and 16 and 17, and so on and so on. Okay, so I'll draw this histogram and then we'll be done for today. So the way it would look is we would have the result of our trial, like our bin size, and this is the number of events in each bin. And so near the mean, we're going to have a lot of events, like maybe the average value is like 18. And so in the bin that has 18 or 19 counts, we'll have a lot of those, maybe like 100 of them or something like that. And then as we move away, the distribution gets smaller and smaller. And so in the tails, there's not much happening in these events. It won't be a perfect bell curve, right? There'll be some fluctuations, but maybe this is our distribution of measurements. Distribution of measurements. What we'll start with on Friday is we'll try to see if we can characterize some properties of this distribution. And the properties are going to be the mean and the standard deviation. I know you know how to calculate those things, but we'll just define those quantities and relate them to how they correspond to this picture. The mean will be the average value. It will sit at the peak of the distribution, and the standard deviation will tell us about the width. Okay, good. Thank you very much. So some of you I'll see in the lab right now, essentially, and then others I'll see on Friday. All right, thank you.